Imagine standing on a shoreline. Not thousands, but hundreds of millions of years ago. The water looks calm, empty, endless. But beneath the surface, something enormous moves. Could predators really have been the size of school buses? Fish longer than cars? Marine reptiles with jaws powerful enough to crush bone like glass? It sounds exaggerated. But long before dinosaurs ruled the land, the oceans were already home to giants. And that raises a powerful question. Why did evolution push marine life toward such massive sizes again and again across completely different species? To answer that, we have to enter a world where oxygen levels shifted, ecosystems collapsed and rebuilt, and survival meant adapting to a battlefield without walls, without shelter, and without limits. This wasn't just the age of strange creatures. It was the age of escalation. One thing we know for certain. Life began in the ocean. For billions of years, it was the only arena where evolution had to experiment in. And the ocean plays by different physical rules than land. On land, gravity dominates. It presses down. It limits size. It demands thick bones and reinforced limbs. But in water, buoyancy changes everything. Water supports most of an animal's weight, which dramatically reduces structural stress on the body. A creature that would collapse under its own mass on land can move almost effortlessly in the sea. This physical advantage opened the door to something extraordinary: gigantism. In prehistoric oceans, being enormous wasn't just imaginable, it was mechanically feasible. And once something becomes feasible in evolution, sooner or later, it gets tested. And just like that, size became more than a feature. It became strategy. Take Endoceras as an example, one of the largest known Ordovician predators. This was not a sleek squid like the ones we imagine today. Endoceras had a long, straight shell, almost like a massive underwater spear, stretching several meters in length. Inside that rigid shell was a soft-bodied, equipped with tentacles used to grasp prey. The shell itself was divided into internal chambers. These chambers weren't empty. They were part of a buoyancy control system. By adjusting the gas and liquid inside them, Endoceras could regulate its position in the water column, rising or sinking with surprising control for such an ancient creature. The fun fact is that this species is not a squid, as you might think. Specialists classify it as an early cephalopod, a distant relative of modern squids, octopuses, and nautiluses. But unlike modern squids, it carried its shell externally, forming a rigid armored body that protected its vulnerable tissues while still allowing mobility. After decades of fossil studies, most researchers agree that some individuals may have reached around 6 meters in length. Others suggest that certain specimens could have exceeded 7 meters. And of course, we will never know the absolute maximum, because Endoceras lived more than 450 million years ago, in oceans so different from ours that even the continents were unrecognizable. What we do know is this: in a world long before fish dominated the seas, before sharks, before marine reptiles, giant cephalopods were already ruling the water. And that tells us something important. Gigantism in the ocean didn't begin late. It began early. There's another piece of the puzzle: oxygen. As we saw, larger bodies require more energy. More energy requires more oxygen. There were periods in Earth's history when oxygen levels were higher than today. Higher oxygen can support higher metabolic demands. Large bodies require large oxygen intake. So yes, chemistry likely removed some biological constraints. But gigantism in the oceans wasn't simply about oxygen. It was also about escalation. When old apex predators declined, ecosystems didn't calm down. They destabilized. And when everything around you is getting tougher, faster, and more dangerous, standing still isn't an option. By the Devonian period, the seas were already filled with heavily armored fish known as placoderms. One of the most famous examples is Dunkleosteus, a predator with massive bony plates and a bite force powerful enough to shear through armor. When prey develops thicker plates, predators evolve stronger jaws. When predators evolve stronger jaws, prey changes to better defenses. Scale escalates. Weapons and armor also escalate. And sometimes the only way to stay competitive is to grow. This evolutionary arms race can escalate quickly. In prehistoric seas, massive marine reptiles did not appear in empty oceans. They emerged in ecosystems already trending upward in size. Once a food web supports large mid-level predators, top predators must grow even larger to dominate them. Not because evolution wants giants, but because pressure pushes it there. There's another advantage to being large in water. Water retains heat differently than air. Large bodies lose heat more slowly, giving them thermal stability, especially in cooler marine environments. Even today, animals like the leatherback sea turtle can maintain body temperatures above surrounding water due to their large mass. Scale provides thermal inertia. In prehistoric oceans, this would have offered clear advantages. Bigger bodies are also more energy efficient over long distances. In vast marine environments where food is scattered, traveling efficiently matters, and in a world of endless water, distance is survival. Size doesn't just intimidate, it conserves energy, it stabilizes temperature, it increases reach. And in prehistoric oceans, all those advantages added up. So at this point, you might be asking yourselves, if gigantism was so powerful, why didn't it continue without limit? Why don't we see even bigger creatures today? And the answer might surprise you, because evolution is not a race toward size. It's a balance between energy, stability, and survival. Gigantic bodies require enormous amounts of food. They depend on stable ecosystems. They demand vast oxygen supplies. And Earth does not stay stable for long. Climate shifts. Oxygen levels fluctuate. Sea levels rise and fall. When the great marine reptiles disappeared at the end of the Cretaceous, it wasn't because size had failed. It was because the world changed faster than they could adapt. But something remarkable happened next. Millions of years later, mammals entered the oceans, and once again, giants emerged. The blue whale is not an exception to the rule. On the contrary, this mammal is proof of the rule. Different lineage, different anatomy, but the same outcome. Fish, reptiles, mammals. Across hundreds of millions of years, completely unrelated groups reached colossal size under the right marine conditions. That repetition tells us something powerful. The ocean does not randomly create giants. It repeatedly enables them. But there is a ceiling. Modern oceans are less oxygen-rich than some prehistoric periods. Food webs are heavily structured. Primary productivity sets limits on how much energy flows upward, and today, human impact adds an entirely new constraint: overfishing, warming waters, habitat disruption. Gigantism is possible, but only when physics, chemistry, ecology, and stability align long enough for evolution to scale up. Right now, those conditions are narrower than they once were. Prehistoric oceans created giants because in the deep water, gravity almost doesn't exist. Buoyancy allows bodies to grow beyond terrestrial limits. Oxygen levels and energy availability sometimes remove biological constraints. Ecosystems reward size as protection and power. And finally, predator and prey push each other upward in an evolutionary arms race. Gigantism was not an accident. It was a solution to instability, to competition, to distance in an endless three-dimensional world. When conditions allow it, the ocean scales up life. Prehistoric oceans did not set out to create monsters. They created opportunity. And history leaves us with one haunting truth. As long as oceans exist, And as long as energy flows through them, there will always be the possibility that something enormous is rising from the deep. What fascinates you most about prehistoric ocean giants? Was it the physics of buoyancy, the oxygen-rich seas, or the relentless evolutionary arms race? Did this change the way you see the ocean today? Share your thoughts in the comments below. And if this journey into Earth's ancient seas expanded your sense of scale, like and subscribe for more explorations into nature's deepest mysteries.